One. Today we will discuss about synthetic polymers. First we will see what introduction of synthetic polymers. Polymer from the backbone of modern civilization and are the chief products of the modern chemical industries in almost all walks of life, starting from household utensils, clothes, furniture, etc. to automobiles to space aircraft and biochemical and surgical operations. Polymer are extensively used. Polymers Greek word है poly means many and meros means parts are very high molecular mass substance, each molecule of which consists of a very large number of simple structural units joined together through covalent bond in a regular fashion. The simple molecules from which the repeating structural units are derived are called monomers, and the process by which these simple molecules, that is monomers, are converted in polymers are called polymerization. For example, polythene is a widely used polymer which is obtained by polymerization of monomer ethylene or ethene. Besides the repeating structural units, a polymer generally contains two types of end groups. For example, in case of polythene, these end groups are CH3, CH2, ethyl and ethanyl CH2 double bond CH groups. Thus, polythene may be completely represented as CH3, CH2, CH2, CH2 bracket close and CH double bond CH2. The nature of the end groups, however, depend upon the method of preparation of polymers, and in many cases the structure of end group are not known with certainty. Therefore, polymers are generally written in the term of recurring units only, that is CH2, CH2N. Polymers and macromolecules. The term polymer and macromolecules are often used without any distinction, but strictly speaking, a polymer always consists of 100 to 1000 of repeating structural units, but a macromolecule may or may not containing repeating structural units. For example, chlorophyll is a macromolecule but not a polymer because it does not contain any repeating structural units. Similarly, protein and nucleic acids should be regarded as macromolecules but not polymers, since their molecules do not contain repeating structural units. In contrast, polythene may be regarded both as macromolecule as well as polymer, since it contains a large number of repeating structural units. Thus, all polymers are macromolecules, but all macromolecules are not polymers. Although protein and nucleic acid are macromolecules, they are usually called polymer. This is due to the reason that protein are made up of a large number of alpha amino acids, which is not structurally or chemically similar. Similarly, nucleic acid are made up of a large number of nucleotides, which are also chemically similar. Homopolymer and copolymers. Depending upon the nature of repeating structural units, polymers are divided into two categories: homopolymers and copolymers. Homopolymers are the polymers whose repeating structural units are derived from only one type of monomer units are called homopolymers. For example, in case of polythene polymer, which is obtained by polymerization of ethylene molecule, the repeating structural unit is derived from only one type of monomer, that is ethylene. Other example of homopolymers are polypropylene, PVC, polyisoprene, neoprene, polyacrylonitrile, nylon 6, polybutadiene, Teflon, cellulose, starch. Second is copolymers. Polymers whose repeating structural units are derived from two or more type of monomer units are called copolymers. For example, in case of nylon 66, the repeating structural unit is derived from two monomer units, hexamethylene diamine and adipic acid. Other example of copolymer are buna S polyesters, alkyd resins, bakelite, melamine, formaldehyde polymer. Classification of polymers. Depending upon the source from which they are obtained, polymers are broadly divided into the following three classes: natural polymers, semi-synthetic, and synthetic polymers. Natural polymers. Polymers which are found in nature, that is in animals and plants, are called natural polymers. Protein, which makes much of our body; nucleic acids, which control heredity at molecular level; cellulose, which provide food, clothing and shelter; and rubber, which is used for making various articles of daily use, are all natural polymers. Semi-synthetic polymers. These are mostly derived from naturally occurring polymers by chemical modifications. For example, cellulose on acetylation with acetic anhydride in presence of concentrated H2SO4 gives cellulose diacetate, which is used for making threads of acetate rayon and other material like films, glasses, etc. Vulcanized rubber, which is superior to natural rubber, is extensively used for making tires, guns, cotton, which is cellulose. Trinitrate is used for making explosive and smokeless powders. Synthetic polymers. A large number of man-made polymers are now available. These include fibers, plastic, rubber, which are widely used for clothing, electric fittings, eyelashes, and as substitute for wood and metals. In this unit, we will shall discuss only synthetic polymers. Preparation of synthetic polymers. The properties of synthetic polymers depend largely on the extent of polymerization. Therefore, to prepare polymers of desired properties, it is essential that the monomer used in polymerization must be of highest purity. The condition of reaction must be carefully controlled. This is because the reaction involved in the process of polymerization must proceed in almost quantitative yields. Any impurity, if present, may initiate an undesirable side reaction which may stop polymer chain from growing further and thus prevent the formation of high molecular mass polymers. The processes involved in the synthesis of polymers can broadly divided into the following two categories: addition or chain growth polymerization, condensation or step growth polymerization. Addition or chain growth polymerization. In this type of polymerization, the molecule of same or different monomers simply add on one another, leading to formation of macromolecule in which the molecular formula of repeating structural unit is the same as that of starting monomer. The polymers thus formed are called addition polymers. These are called chain growth polymers. Addition or chain growth polymerization generally occurs among molecules containing carbon-carbon double bond. The reaction is started by a suitable initiator which adds to the carbon-carbon double bond to form a reactive intermediate. This reactive intermediate then adds to the second molecule of monomer to form a new bigger intermediate, which in turn add to third monomer molecule, and so on. In this way, the polymer chain keeps on growing by successive addition of monomer molecules, one at a time, to the reactive end of the chain. That is why this process is called chain growth polymerization. Since most of the monomer used in addition or chain growth polymerization are monosubstituted alkenes, that is vinyl derivatives, therefore addition or chain growth polymerization is also called vinyl polymerization. Some of the most important polymers formed by vinyl polymers are polythene, propylene, PVC, PAN, polystyrene, polymethyl methacrylate. Depending upon the nature of monomer taken and the initiator used in the above polymerization, the reactive intermediate may be a free radical carbocation or a carboanion. Therefore, vinyl polymerization occurs by three different mechanisms. Let us now discuss in detail the mechanism of addition or chain growth polymerization by starting with free radical vinyl polymerization. Free radical vinyl polymerization. Most of commercial addition polymers are vinyl polymers which are obtained by polymerization of alkene derivatives. This type of polymerization is carried out by heating the monomer with a very small amount of radical initiator or by subjecting the monomer to ultraviolet light. These initiators are molecules which decompose to form radicals easily. Tertiary butyl peroxide, benzoyl peroxide, and azido diisobutyronitrile are commonly used as initiators because they decompose under mild condition to form radicals. Like all other radicals reaction, free radical polymerization also occurs through the following three steps: initiation, propagation, termination. Chain initiation step. The initiator on heating decomposes to form initiator free radicals. The process of polymerization starts with the addition of the initiator free radical to double bond of alkene monomer to form a new free radical of large size. Chain propagation step. The addition of radical first to another molecule of alkene generate yet another bigger sized radical second. The repetition of this sequence with new and bigger sized radicals propagate the reaction, and these steps are called chain propagating step. Chain termination step. Eventually the polymer third is terminated by reactions that consume three radicals either by combination or by disproportion. Many other simple and substituted alkenes such as propylene, vinyl chloride, styrene, tetrafluoroethylene, acrylonitrile, methyl methacrylate, vinyl acetate, etc. Chain transfer agents. Competing reaction in vinyl polymerization. We have discussed above that during vinyl polymerization, the termination step involves either combination or disproportion of growing radical chains. However, the growth of original polymer chain may also get terminated or interrupted in presence of certain compounds such as CCl4 which compete with the monomer for growing polymer chain. At the same time, such a compound produces a new free radical which may initiate its own new polymerization chain. The overall effect of such compounds on the process of polymerization is that the polymer formed has lower average molecular mass. Such compounds which bring about the termination of original polymer chain with the simultaneous initiation of another polymer chain are called chain transfer agents. For example, in the presence of CCl4, styrene undergoes polymerization at the same rate as in its absence, but the polystyrene formed has a lower average molecular mass. Furthermore, it also contains small amount of chlorine. This may be explained as follows. The growing polystyrene radical first, which would normally react with another monomer molecule, instead reacts with chain transfer agent to terminate the original chain, and the new free radical produces initiates a new polymerization chain incorporating chlorine atom. Since one reaction chain is replaced by another, the rate of polymerization is unaffected. Further, since the average number of chain propagating steps in each reaction chain is reduced, the average molecular mass of polymer decreases. Chain inhibitors. If the chain transfer agent forms a radical which is highly unreactive, the original reaction chain gets terminated without the new being initiated. As a result, the process of polymerization is inhibited. Such chain transfer agents which inhibit the process of polymerization are called inhibitors. Many amines, phenols, and quinones act as inhibitors, since even traces of impurities of chain transfer agents or inhibitors can interfere with the polymerization process. Therefore, monomer used should be highly pure organic compounds. In the extreme case, if the monomer is of low reactivity, the chain transfer agent is of highly reactivity, then no polymerization occurs. Instead, addition of chain transfer agents occurs across the double bond of monomer. Ionic vinyl polymerization. This type of vinyl polymerization proceeds through ionic intermediates, carbocation or carboanions instead of free radicals. It is further classified are cationic vinyl polymerization and anionic vinyl polymerization according as carbocations and carbanions respectively are the intermediates as described below. Cationic polymerization. Certain alkenes monomers can be polymerized by a cationic mechanism as well as by free radical mechanism. Cationic polymerization, like free radical polymerization, occurs by a chain reaction pathway in presence of a strong protonic acid such as H2SO4 or Lewis acid such as AlCl3, BF3 in presence of trace of water as initiator. In the chain initiation step, a proton adds to the double bond of the monomer to form a carbocation. In the propagation step, the electrophilic addition of this carbocation intermediate occurs to the double bond of another monomer molecule to form a bigger carbocation. This sequence of steps is repeated over and over again to form a polymeric carbocation. In the chain termination step, the loss of a proton from the polymeric carbocation occurs to complete the polymerization. This is the chain initiation step, chain propagation step, chain termination step. Evidently, greater the stability of carbocation intermediate, more facile is the cationic polymerization. Thus, alkenes containing electron donating groups are preferably polymerized under cationic conditions, although free radical polymerization can also occur. In contrast to monomer such as vinyl chloride and acrylonitrile, which contain electron withdrawing substituents, do not polymerize well under these conditions. This is because the presence of electron withdrawing substituents destabilize the carbocation intermediates. Anionic polymerization. Alkene monomer with electron withdrawing substituents such as C6H5CnCOO are can be polymerized by an anionic mechanism as well as by a free radical mechanism. Anionic polymerization, like free radical polymerization, occurs by a chain reaction pathway in presence of strong bases such as Na positive, NH2 negative, Li positive, NH2 negative, or organometallic compounds such as N-butyl lithium as initiator. In the initiation step, the base adds to double bond of the monomer to form a carbon anion. In the propagation step, this carbon anion adds to another monomer molecule to form a bigger carbon anion, and the process gets repeated over and over again to form a polymeric carbon anion. This chain reaction is finally terminated by addition of a proton. Some alkanes are easily polymerized even by weak bases, for example methyl alpha cyanoacrylate, because of presence of two powerful electron withdrawing group. CN and CO2CH3 quickly undergo polymerization even in presence of basic impurities such as metal oxides present on the surface of ordinary glass to give superglue or crazy glue. It has high tensile strength. One drop of its claimed to support a weight of 2000 lbs. Evidently greater the stability of carbon anion intermediate, more facile is the anionic polymerization. Thus, alkane containing electron withdrawing groups such as acrylonitrile, methyl acrylate, styrene can be polymerized under anionic condition, although free radical polymerization is commercially preferred. Limitations of vinyl polymerization. Although vinyl polymerization can take place by free radical or ionic, cationic or anionic mechanism, it is usually carried out by using free radical initiators. This kind of polymerization suffer from the following two drawbacks. Branched structure of polymers. Free radical polymerization does not give linear polymers but instead gives branched chain polymers. The presence of these branches influence the properties of polymers. In general, branch chain polymers do not fit closely and hence have low melting point, low degree of crystallinity, and have weak mechanical properties. Stereochemistry of polymers. Free radical vinyl polymerization involves head-to-tail union of monomer units. As a result, the substituent groups appear on the alternate carbon atom of the polymer chains depending upon the relative position of group G on the polymer chain. Three stereochemical arrangements are possible as given below. Isotactic. In this arrangement, all substituent group G lie on the same side of zigzag chain. Syndiotactic. In this arrangement, substituent group G regularly alternate on opposite sides. Atactic. In this arrangement, substituent groups G are randomly oriented. For any particular polymer, the three stereoisomeric forms have somewhat different properties. In general, isotactic and syndiotactic polymer fit together well and high degree of crystallinity. They have high melting point, have stronger mechanical properties, and form strong fiber. In contrast, atactic polymer are soft, elastic, rubbery materials. By a proper choice of experimental conditions such as catalyst, temperature, solvent, each of these stereoisomeric polymers can be prepared. Free radical vinyl polymerization generally gives branched atactic polymer. However, isotactic and syndiotactic polymer can be made by use of special Ziegler-Natta catalyst. Ziegler-Natta polymerization. Until 1953, almost all vinyl polymerization were carried out by free radical initiators. Since then, a new kind of polymerization called coordination polymerization was introduced by Carl Ziegler and Natta, who jointly received the Nobel Prize in 1963 for this work. Coordination polymerization is carried out in presence of Ziegler-Natta catalyst, which consists of titanium trichloride or tetrachloride and an alkyl aluminium compound. The most commonly used catalyst of this type is the mixture of ethyl aluminium and titanium tetrachloride Al2H5 whole 3 plus TiCl4 in an inert solvent such as heptane. The solution is then heated for an hour. There are three main advantages of using Ziegler-Natta catalyst. Polymerization takes place under relatively milder conditions. The polymers obtained are linear with almost no branching. The polymerization occurs in a stereospecific manner. It is possible to prepare either the isotactic or syndioctic polymer by a proper choice of Ziegler-Natta catalyst. Mechanism: when triethyl aluminum and titanium chloride are mixed, they form a titanium complex holding an ethyl group. When an alkane, say ethylene, is added to this mixture, it forms a coordination complex with the transition metal titanium. By donating its pi electrons, that is, the pi cloud of alkene overlap with an empty d orbital of titanium. Now both ethyl and ethylene molecule are held by metal. An insertion reaction occurs in which the ethylene molecule is inserted between the metal and ethyl group. In other words, instead of ethyl, there is now an butyl group attached to titanium. The binding site where the ethylene was held earlier is now vacant. Another ethylene molecule gets pi bonded to the metal and then inserts itself between the metal and n-butyl group to form this time n-hexyl group. So the process continues over and over again with the alkyl group growing 2 carbon atoms at a time. Ultimately, insertion of hydrogen occurs either by hydrogenation or beta elimination, and the molecule of polythene gets separated from the metal. Some important vinyl polymers: polythene or polythene, polyethylene or polythene. It is widely used addition polymer and was first prepared by free radical or high temperature polymerization of ethylene. However, these days two types of polythene are produced which have widely different properties. These are low density polythene and high density polythene. Both these polymers, however, have the same repeating structural units. Low density polythene, it is manufactured by heating ethylene to 350 to 570 Kelvin under a pressure of 1000 to 2000 atmospheres and in the presence of a trace of oxygen or peroxide. This polymerization occurs by a free radical mechanism which is initiated by oxygen or peroxide. The polythene thus produced has a molecular mass of about 20,000 and has highly branched structure. This branching occurs due to chain transfer of a special kind in which the chain transfer agent is a polymer molecule at the high temperature at which this polymerization occurs. The growing free radical not only add to the double bond of monomer but also abstract hydrogen from a chain already formed. This abstraction generates a new free radical center from which a chain can now grow as shown below. These branched polythene molecules do not pack well and hence this type of polythene has a low density 0.92 gram per centimeter cube and a low melting point 384 Kelvin. That is why polythene prepared by free radical polymerization is called low density polythene. Properties and uses: low density polythene is a transparent polymer of moderate tensile strength and high toughness. It is chemically inert, slightly flexible, and is a poor conductor of electricity. It is widely used as packing material in the form of thin plastic film bags, as insulation for electrical wires and cables, in manufacturing of squeeze bottle, toys, and flexible pipes. Highly density polythene. It is prepared by coordination polymerization of ethylene. In the process of ethylene in a hydrocarbon solvent, it is heated to 330 to 350 Kelvin under pressure of 1 atmosphere in presence of a catalyst consisting of triethyl aluminum and titanium chloride or tetrachloride Ziegler-Natta catalyst. The polythene thus produced practically consists of linear chains of polymer molecules. These polymer molecules pack well and hence this type of polythene has high density 0.97 gram centimeter cube and higher melting point 403 Kelvin than the polymer produced by free radical polymerization. That is why polythene prepared by coordination polymerization is called high density polythene. Properties and uses: high density polythene is a translucent polymer. It is a chemically inert but has greater toughness, hardness, and tensile strength. Polyethyl acrylate preparation. It is prepared by free radical polymerization of ethyl acetate NCH2 double bond CH C2H5. Ethyl acrylate is treated with peroxides gives polyethyl acrylate. Properties and uses: polyethyl acrylate is a tough and somewhat rubber-like product. It is mainly used in manufacture of blanket, carpets, and variety of clothes. Polyacrylonitrile, also known as PAN, preparation polymerization of acrylonitrile vinyl cyanide in presence of peroxides or FeSO4 and H2O to catalyst Q. Polyacrylonitrile. The monomer acrylonitrile is itself manufactured either by addition of HCl to acetylene in presence of CuCl, HL as catalyst, or by passing a mixture of propylene, ammonia, and air over a catalyst consisting of mixture of oxides of molybdenum, cobalt, and aluminium at 723 Kelvin. Uses polyacrylonitrile is a hard, horny, and high melting material. Condensation or step growth polymerization. In this type of polymerization, a large number of monomer molecules combine together, usually with the loss of simple molecules like water, alcohol, ammonia, carbon dioxide, hydrogen chloride to form a macromolecule in which the molecular formula of repeating structural unit is generally not the same as that of monomer. The polymer thus formed are called condensation polymers. Condensation polymers generally occur between monomers containing bifunctional and polyfunctional compounds. For example, the polymer nylon 66 is obtained by the condensation of two monomers. Actually, condensation polymerization occurs through a series of independent reactions. Each such reaction involves the condensation between two dysfunctional monomer molecules, the loss of simple molecules like H2, NH3, ROH, HCl to form a dimer, which is also a bifunctional compound. That this dimer may react with the another molecule of one of the monomer, and the resulting product may react with another molecule of second monomer to form a tetramer. Thus, the products at each step are again dysfunctional compounds, so that the sequence of condensation reaction goes on and the polymer chain keeps on growing step by step. Alternatively, the dimer may combine to form tetramers, which in turn may combine to form octamers, etc. These molecules of moderate size then combine together to form the polymer chains. In the process, the polymer is formed in a stepwise manner. It is called step growth polymer, and the process is called step growth polymerization. For example, formation of nylon 66 may be depicted as follows. It may be pointed out here that in contrast to chain growth polymers, the formation of step growth polymers does not occur through chain reaction involving free radicals, carbon anions, or carbocations as reactive chemical species. Polyesters. Polymers which have ester linkage are called polyesters and are prepared by condensation of polymerization of diacids with diols. Two important polyester polymers are discussed below. Polyethylene terephthalate, Dacron-Miller preparation. It is prepared by condensation polymerization of ethylene glycol and terephthalic acid with elimination of water. The reaction is carried out at about 420 to 460 Kelvin in presence of catalyst consisting of a mixture of zinc acetate and antimony trioxide. Uses. The fiber of terephthalate is highly grease resistant, durable, and has low moisture content. It is also not damaged by pests like moths and mildew. It is therefore used for manufacture of wash and wear fabrics, tire coats, sheet belts, and sails. It is also blended with cotton and wool to increase their resistance to wear and tear. The mylar film is extremely flexible, tear resistant, and resistant to ultraviolet degradation. It is therefore used for making magnetic recordings. Polyethylene phthalate, glyptale, or alkyl resin. Glyptale is the general name for the all polymer obtained by the condensation of dibasic acids or their anhydrides with a polyhydric alcohol such as ethylene glycol glycerol. The simplest glyptale is formed by the condensation of ethylene glycol and phthalic acid. Uses. It is a thermoplastic. It is all insoluble solvent and the solution on evaporation leaves a tough but not flexible film. It is therefore used in the manufacture of paints and liqueurs. Polyamides Polymers which have amide linkage are called polyamides. These are prepared by the condensation polymerization of dibasic acids with diamines or their equivalents. These polymers are commonly called nylons. The name nylon is given to these fabric fibers since the most common nylon 66 was simultaneously prepared in New York and London. Nylon 66 preparation. It is manufactured by the condensation polymerization of adipic acid and hexamethylene diamine. The acid and the amine first react to form a salt which when heated at to 525 Kelvin under pressure undergoes polymerization with elimination of water as steam, and the nylon is produced in the molten step. It can then be cast into a sheet or fiber by passing through a spindle. It is called nylon 66 since both adipic acid and hexamethyldiamine contain 6 carbon atoms each. Uses unlike cotton fibers, nylon fiber do not have high tensile strength, are tough, abrasion resistant, and somewhat elastic. These are therefore used in the manufacture of carpet, textile fiber, and bristles for brushes. Further, nylon fibers are so much stronger than the natural materials that these can be made much thinner. The availability of such a strong, thin thread made possible nearly invisible woven stockings called nylons. Being tough, nylon is used as a substituent for metal in bearing and gears. Crinkled nylon fiber are used for making elastic hosieries. Nylon 610. Another commonly used nylon is nylon 610, which is obtained by the condensation of hexamethylene diamine containing 6 carbon atoms and sebacic acid, a dibasic acid containing 10 carbon atoms. Nylon 6 or Bedlon preparation. Nylon can be also be prepared from a single monomer having a potential amino group at one end and potential carboxyl group at the other. For example, the monomer caprolactam on polymerization gives nylon 6. Caprolactam needed for this process is manufactured from cyclohexene, a petrochemical as described below. When caprolactam is heated with a trace of water, it undergoes hydrolysis to give amino caproic acid, which upon continued heating undergoes polymerization to give nylon 6. It is manufactured by most of the industries in India. It is called as nylon 6 since the monomer contains 6 carbon atoms. Uses. It is used for manufacture of tire coats, fabrics, and mounting ropes. Phenol formaldehyde resin. Reaction between phenol and formaldehyde has been used for the manufacture of an important group of polymer commonly called as phenol formaldehyde resins such as Novolac and bakelite. When phenol is treated with formaldehyde in the presence of an acid or basic catalyst, it undergoes condensation polymerization to form either a linear or cross-linked polymer called phenol formaldehyde resin or bakelite. The process actually involves formation of methylene bridges either at ortho or para position or both at ortho and para position with respect to the phenolic group. The initial product is a linear polymer called Novolac, which upon further heating with formaldehyde undergoes cross-linking to form an infusible solid called bakelite. Uses. Soft bakelites with low degree of polymerization are used as binding glue for laminated wooden planks and in vernices and liquids. High degree polymerization leads to formation of a hard bakelite which is highly cross-linked and is thermosetting polymer. It is a scratch and water resistant polymer and hence is used for the manufacture of combs, formica tables, tops, fountain pen barrels. Sulfonated bakelites are used as ion exchange resins. Natural rubber. It is a natural polymer which is obtained from latex. Latex is a milky fluid which exudes from the rubber tree when an incision is made in the bark of rubber tree found in the tropical and semi-tropical countries such as southern India, Kerala, Tamil Nadu, Karnataka, Indonesia, Malaysia, Sri Lanka, South America. Latex is a colloidal solution of rubber particle 30 to 40% which is coagulated by adding salt and acetic acid. The coagulated material is passed through the roller and makes sheets. Since it is repeating unit in polyisoprene containing a double bond, it may have either a cis or trans orientation. Actually, in natural rubber, the double bonds have cis stereochemistry. In other words, natural rubber is cis polyisoprene. In contrast, synthetic rubber obtained by free radical polymerization of isoprene has all trans configuration. Vulcanized rubber inspection of structure of natural rubber reveals that there are no polar group substituent and hence intermolecular forces of attraction are only weak under wall interaction. These forces are further weakened because of cis configuration of all double bonds which does not allow the polymer chains to come close enough for effective interactions. The cis polyisoprene does not have a straight chain but has a coiled structure. As a result, it can be stressed like a spring. On stressing, the molecule become partially aligned with respect to each other, and on withdrawing the force, the chain come back to their original coiled state. Natural rubber is soft and tacky and become even more so at high temperatures and brittle at low temperature. Therefore, rubber is generally used in the temperature range 283 to 335 Kelvin where its elasticity is maintained.